Hello friends, welcome to my YouTube channel. The title of my today's video is Power Set of a Set from a Different Perspective. In this video, we try to visualize the power set of a set from an entirely different viewpoint. Given any two sets x and y, consider the set y to the power x of all functions from x to y. So y to the power x is the set of all functions from x to y. The set y to the power x can also be thought of as the generalized Cartesian product like this, where each yx is equal to y. There are as many y's here as there are points in the set x. Capital X is serving as an indexing set in this Cartesian product. The elements of these Cartesian products are written as like this, where each small y x is an element of y. There is a bijective map from y to the power x to this Cartesian product, and that's why this set can be thought of as this Cartesian product because of this bijective map. What is that bijective map? It takes an arbitrary element. Suppose f is an arbitrary element of this set. That means f is a function from x to y. Then it goes to product of these elements fx as x runs over x, capital X. Okay. So this element here looks like this element, where in place of y suffix x I have taken fx. So this is an element of this Cartesian product. And what is the inverse of this map? So inverse of this map is a map from this Cartesian product to y to the power x. So we start with an arbitrary element here in this Cartesian product yx, where x is in x runs in x, and it goes to h. And what is h? H is given by this definition. Hx is equal to yx for all x in x. So this yx is this starting point here. It comes from here. And you can easily check that this is actually a bijection. This map is a bijection. This is actually an inverse. Okay. So if you start with this f here, it will go to fx, and then what is h of where does this product go under this map? So it will go to hx will be equal to, in place of yx we have to put fx. So hx will be equal to fx. That means h will be equal to f. So this h will be equal to f. So in this way the other side also can be proved. So this becomes a bijective map. This map becomes a bijective map with this inverse. In particular, if we take x to be the set of natural numbers, then this Cartesian product can be written as y cross y cross y and so on. Okay, this is the usual notation for Cartesian product. And its elements, these elements can be written as a sequence, y1, y2, y3 and so on. So this situation arises when x is taken as the set of natural numbers. Also, if x is taken as this finite says 1, 2, 3 up to m for some natural number m, then this product can be written as y cross y cross y m times, and its elements, this becomes, instead of sequence, it becomes m tuples like this. Thus a function f from n to y, that means f is an element of y to the power capital N, can be visualized as a sequence like this, f1, f2, f3 and so on of elements of y. So a function can be, this type of function can be visualized as a sequence of elements of y. Okay. Also, a function f from this finite set to y can be visualized as an m tuple f1, f2, up to fm of elements of y. So, both these things are because of that bijective correspondence between y to the power n and Cartesian product of y taken n times. Okay. Now let us put y equal to this doubleton set or two element set 0, 1. So earlier we started with y to the power x. First we replaced x by n, and now we are replacing y by this doubleton set. In that case, the set y to the power x becomes this doubleton set to the power x, and it is denoted by 2 to the power x. So instead of writing this doubleton set 0, 1, we write 2. So it is written as 2 to the power x. There is a bijective map from the power set px to 2 to the power x. So from the set of all subsets of x to the set of all functions from x to this doubleton set, there is a bijection. And this bijection is given by, you start with an arbitrary subset of x, that is capital A, and send it to a function from x to 2, which is given by chi suffix a. And what is chi suffix a? Chi suffix a is a function from x to this doubleton set 0, 1, and it is defined by this formula. Chi x of x is equal to 1 whenever x belongs to A, and it is equal to 0 whenever x is outside A. So this small x is an element of capital X, but whenever it is inside A, chi A of x is 1, but whenever it is outside A, it is 0. This chi A, okay, this mapping chi A is called the characteristic function of A. The inverse map from 2 to the power x to px of the above map from px to 2 to the power x. Now, which map we are talking about? We said that there is a bijective map from this power set to x. So bijective map means there is an inverse from this to this also, 2 to the power x to this. Direct map is given like this, A going to characteristic function of A. How about the inverse map? Inverse map is given by inverse map from 2 to the power x to px of the above map from px to 2x is given by start with an arbitrary element of 2 to the power x, that means start with a function from x to doubleton set 0, 1, suppose this is f, and send it to this set of all x in x such that fx equal to 1. Okay. So f going to this set. So this is a subset of x, and this is inverse map of this, because if you start from this set, then send it to characteristic function of this set, and characteristic function of this set is actually our small f. You can readily check it. Okay. In particular, putting x is equal to natural number. Now our y is 0, 1, and x also, so far it was arbitrary, but now we take x to be equal to set of natural numbers. So in that case, actually now we are talking about 2 to the power n. So we are, instead of 2 to the power x, we are talking about 2 to the power n. So there is, in the previous page you have shown that there is a bijection from 2 to the power x to px. So there is a bijection from 2 to the power n to pn. So, or pn to 2 to the power n. So we start with an element of pn. So an element of pn, for example, let us take this one, 3, 5, 9. This is a 3 element set taken in Pn. So this is a subset of natural numbers, So under that bijection, how does it look like when you consider it as an element of 2 to the power n? It looks like this function f from n to 0, 1, and it is given by 3, 5 and 9 goes to 1 under this function, and all other natural number go to 0. And this 2 to the power n is again bijective to the Cartesian product of here y is 0, 1. So Cartesian product of all these doubleton sets, product taken as many times as there are natural numbers. Okay. So that means we are talking about sequence consisting of zeros and ones. So this function, when you consider it as a sequence containing sequence having 0 and 1 as its elements, then this particular function will look like this sequence, where we have 0 and 1 only, 1 in the 3rd position, 5th position and 9th position, okay, and zeros everywhere. So this particular set 3, 5, 9 looks like this particular sequence. Okay. So subsets of Pn, any other subset, if you take say entire set 1, 2, 3, 4, 5, 6 and so on, so that will have 1 in every position, because we are talking about all sets. If you take set of subset consisting of all even numbers, then we will have 1 in the even position, that is first position will be 0, then 1, 0, 1, 0, 1, like that it will go. Okay. In an earlier video, we have seen that there does not exist any onto map from x to px. From x to power set of x, there is no onto map. Therefore, we can say that there does not exist any onto map from x to 2 to the power x also, because px and 2 to the power x are bijective to each other. Now, this particular fact can also be established directly by assuming the existence of an onto map g from x to 2x, 2 to the power x, and asking whether the following element of 2 to the power x has a preimage under g or not. What is that element of 2 to the power x? It has to be a function from x to 2, x to doubleton set 0, 1, and we are talking about this function. And what is this function? H from capital X to 0, 1 defined as hx is equal to 1 if gx x equal to 0. Now, what is g? G is a mapping from x to 2 to the power x. So, image of g, image of any element under g is also a mapping. So, if you start with small x here, gx will be an element of 2 to the power x. So, gx will be a function from x to doubleton set 0, 2. So, we can talk about gx of an element of x. So, in particular, I take gx of x itself. So, I can talk about gx of x. So, if this gx of x is equal to 0, then we take value of hx to be 1. And if gx of x is 1, then we take hx equal to 0. That means at every point x, we make sure that hx is not equal to gx of x. Okay. And we ask whether this h has a preimage under this map or not. Okay. And this can be readily checked if we say that, okay, if there exists a z such that this h has a preimage, z is the preimage of this h under g. That means if there exists z such that gz is equal to h, then what about gz of z? Gz of z will be equal to h of z, but gx of x is never equal to hx. So, gz of z cannot be equal to hz. So, this contradicts the definition of h actually. So, this h cannot have a preimage, and that is why there cannot be a onto map from x to 2 to the power x. Okay. So that's all in this video. Thanks for watching.